basically the 2,3 butane diol we were discussing last time. I told you take it as a homework, right? And we said how many stereo centers does it have?
Four.
Stereo centers.
Two.
Two. That how many possible isomers?
Four.
Right? We said normally you build one, okay, and then you find the mirror image of it. So these two are they're mirror images of each other, right? They're enantiomers. Okay. Now, is there any symmetry to this?
No.
So the peak is the way you can look at it. I don't see any, but also you can try to superimpose them. Can you superimpose them each other?
No.
You can try to rotate or upside down. You never can get them superimposed, right? What happened to the third element that we mentioned?
We switched to one.
So we switch one. So which one do you guys want to switch?
Any red with any white.
So we switch this one here. Goes here. Doesn't matter which one you switch actually, just one of them. Don't switch one from the top and one from the bottom. That will make a difference. Okay, now these are also enantiomers. Okay? They are mirror images of each other, okay? Do you see symmetry in this?
Yes.
So if you cut this in half, you can see symmetry. Now, what it means that these are superimposable, okay? How can I superimpose them?
Rotate.
Those strands, I'm just kidding. As you can see here. Basically, if you can see here, they are, just get them to fit is not that easy. But basically they are, red on red, red on red. Okay? They're actually the same molecule. The other thing is, you see this molecule right here? This one, are they the same?
Yeah.
They're the same molecule.
Yeah.
Okay? So in theory, you should have 4 possible isomers. But when you actually construct them, you only have 3. Because the 4th one is just the same as the 3rd one. Because there is a plane of symmetry, it's a meso compound, okay? So technically if you build in theory there is 4, but only 3 are possible. And the 3rd one is a meso compound, or basically it's achiral because it has a plane of symmetry. So you can cut this into a half, although they are mirror images of each other, but they're not chiral, okay? They can be superimposed, or if you flip it, it's the same molecule again. Here mirror images, which looks like an enantiomer, is here, that's the same molecule, okay? So I'll pass this around. Don't mess it up like that in class, okay? So any questions on this? This is the assignment you're supposed to do for today, okay? So like I told you, we have 4 possible, because of 2 stereo centers, it's for in-class discussion, not the homework, okay? We have 4 possible, but not always that means they're all going to be actual isomers. So if you have a plane of symmetry, especially with 2, normally it's going to have a meso compound, which means that the mirror image of it is identical to the actual compound. So in this case, we only have 3 instead of 4. Okay, now, in general, the way we tell how many stereoisomers are possible, we said we count how many stereocenters do we have, and we say 2 to the number of stereocenters, 2 to the n, right? So for this is cholesterol, okay? How many stereocenters does it have? 8, right? If you count these stars,
8.
it is 8. How many possible isomers should you have?
256.
I know you read it. Basically, it's 2 to the 8, which is 256, right? Okay?
This is too much.
This is too much. But however, what's so unique about nature, and of course, the creator, is in human, only one of these exists, which is this one.
Wait a minute, what is that?
This specific isomer is the cholesterol that we have as humans. So this is the general structure for cholesterol. But depend, for example, you can have here RNS, here RNS. So for example, if I change one of them RNS, it makes it different from all the 256. If you change 2, it'll make it also, if you change 3, 4, it versus and so on. So there is total of 256, okay, that are possible. Okay? What I'm saying is from those 256, only one of them exists in human, which is this stereoisomer that basically the OH here is what? This is actually an S if you do all of them. You don't have to do all of them. I'm just saying that there's 256 possible, but only one exists in human. Okay? Oops. So what I mean, it's basically they are very specific. Okay? There's 256 that actually exist, but what's found in human is actually this one, the one that shows with the stereochemistry. Here I'm not showing the stereochemistry because I'm just putting the O as a straight line. It's not toward us or in the back. Okay? Because there is the two possibilities of two isomers for each one. All right. So this is what I'm going to demonstrate. Although there's 256, only one exists in nature for human. Okay? So animals may have a different one too. So the other thing that maybe we talked about this last time. So we talked about chirality before. I guess we'll visit again today. And we said the chiral molecule normally what? It has this asymmetric or lack of symmetry, and normally it has 4 different groups around it. Okay. Now another way to test if a molecule is a chiral is we have to find basically to experimentally find if it's optically active. So what it means by optically active, that means it will rotate basically the plane of polarized light. So this is basically what this slide is about in the next slide. So in general, when you have a light, how does the direction of the light go?
Everywhere.
Basically, all over. It has no direction, a specific direction. It's all over the place, basically. Okay. So regular light basically evaporates in all planes. Okay. However, if you have plane polarized light, basically it will be in one direction. Okay.
What is that?
Like laser?
I will show you a picture in just a minute. That means if I pass this light through basically a polarized plane, right? Like a laser, for example, it will go basically just in one direction. It's not this. So basically, if I pass it through here, I'm not going to see basically lights that goes to the sides and everywhere. It's only going to be a straight line with the same parallel light throughout until basically it ends. So basically in parallel lines or planes, or you can call them waves if you want. So one of the instruments that actually does that is a parameter, okay, which basically has a plane, basically a polarizer that makes basically polarized light. And normally, if you put a sample inside this parameter, if the sample actually rotates, okay, the polarized light, it basically go either to the right or to the left, that indicates this sample is optically active. If it doesn't, that means it's not active, which is basically not chiral. Okay, chiral or non-chiral, okay? So optically active compounds are also used for chiral compounds. So when you see optically active means also it's chiral, or vice versa. Okay. And so optically active showing that compound is capable of rotating the plane of polarization. So what does this really mean? This picture hopefully will help. Okay. As you see the source of the light, you can see the light goes all over the place, right? When you pass it through a polarizer filter right here, as you can see these lines right here, and there's the zero angle, basically it's just going to be straight throughout, okay? Now this is your sample, that's where normally the sample is, okay? Now it depends if the sample basically is going to rotate. You can see here, instead of having these straight up and down, what happened is that after they pass through the sample? They rotate in a specific direction, right? So this means this sample is capable of basically rotating polarized light, which indicates this sample must be chiral or optically active, okay? If it's achiral, it will do nothing. This continues as basically as it will continue throughout the insert.
But sir, I didn't understand. Why would the other one rotate?
We'll get to it in just a second, okay?
Where is the compound? Where is the compound?
The sample could be any chiral sample, basically, okay?
Where is it? In this.
And this one, I don't know. This is just a picture. But what I'm saying, you can put any chiral compound. You can put basically glycerol. You can put amino. It doesn't really matter which one. So the key here is the one thing that you should know is normally when you have enantiomers, okay, they are mirror image of each other. If I have one is R, what would be the other one?
S.
S would be the opposite configuration. Okay. So one of them is R, one of them is S. Okay, it's always going to be the opposite configuration. what happened that if you have a specific enantiomer, one of them will basically rotate one way, the other one will rotate
The other
the
one.
opposite. Okay? Does that make sense? But which kind of compound is for specific this one? I really don't know because this is just a picture that I took. Just to do that, the book provides actually.
I
To
mean,
show
where,
as an
where should
example.
we put the compound?
Oh, the compound is actually here.
That's my question.
Oh, that's the.
Yeah.
I thought you were saying me. What compound is this?
Where is the
No,
compound?
no, it's here. Basically, the light has to pass through it
Through that
to be rotated. Okay. I thought you said what compound do we have? All right. So now, basically, we're gonna use a different terminology. So R and S, it comes originally from Latin. It's different from right versus left. But the way it works is basically, I think I call it. You guys know what the Latin word for right and left? I think it's rectus for right, if I'm not mistaken.
Oh my God.
I think it's rectus means right in Latin, and sinister for left. That's where RNS came from. Double check. I think that's where it comes from. So that's why when we said clockwise, that's the R, counterclockwise is the S. Here we're going to talk about basically if it's, this is the 0, right? If it's going to polarize basically to the clockwise, we call this positive. Okay? It's going to be a positive number, or we say plus. If we go to the other way around, it'll be a negative, okay, from the plane of the polarized light. And that will actually, it doesn't matter if it's in R and S, it doesn't really matter, okay? But what we know is this sample is optically active. Here's, for example, how this actually comes around. So basically, in this term, which we will deal more when we talk about carbohydrate, which is the next chapter, actually next week or probably it's on Thursday. So a compound that basically rotate clockwise, we give it the plus. Okay? So from the plane polarized light, this is a 0. If we pass it through the sample and it rotates this way, the polarized light, clockwise, basically it's a positive. We say plus. If it goes the other way around, it's basically negative. That's all we care about at this point. Okay? So, and this is actually means right and left also. Dexteratory versus laboratory means the right or the left. Okay? But we care about the plus and minus. And normally you get a specific rotation. We call that alpha is a specific rotation for a specific sample or optically active. So it will polarize the light by a specific angle. Some of them might be 2, 3, 5, 10, 20, depending on the sample, how far. How do we know that? We have to do the experiment. You can't really predict that. Okay? If you look at, for example, here, lactic acid, okay? You have the S isomer and you have the R isomer of lactic acid, okay? If you put each one separately in the instrument, the parameter, you get a reading for the S plus 2.6. What does that mean? That means if the light was polarized to, it rotated the polarized light into basically clockwise. That's what it means by plus, okay? And the R is minus, that means it's the other way around, okay? Now, is it always going to be the R negative and the S negative and the S plus? No, it depends on the sample, okay? But what I mean, the only important things that you can have, when you have an enantiomer, the mirror images of it is always going to be the opposite configuration. If you have R and S, okay? Now, if they ask you, normally the rotation is equal. So if they have the R, it rotates 10, the S will rotate minus 10. They're always going to, if they are pure. Now, if I told you, if you have a mixture like ibuprofen, so the drug, so how would they call it? It's a mixture, has 50% R, 50% F. If you put it in here, what would happen?
It will stay the same.
Nothing would happen.
Nothing will happen. They cancel each other. Okay. So for mixture of R and S, 50-50, they're called racemic mixtures. Okay. Racemic means 50-50. Therefore, they don't really change the polarized light because they just cancel each other. Each one of them is active, but when they're together, they cancel each other. Okay. However, if you have 75-25, then what happens?
75.
If one of them doesn't really which one. It will move to one direction, the one that has the
It
most.
will overpower.
But if the standard is 10, it's not going to move all the way to 10. It's going to move maybe to 5 or 6. It's based on how much is excess of one enantiomer, which is called enantiomeric excess. But it's beyond this course, yes.
So alpha exponent 21.
What is that?
Alpha squared D.
So-
What is that?
Yeah, this is basically the specific rotation for this sample. So the specific rotation for this is basically, it will move from the 0 by 2.6 degrees.
Yeah, I understand that, but what is before the equal sign?
You mean the 21D?
Yes.
I think it's sometimes it's used based on the temperature when this was taken. It indicates the temperature. A lot of times it's taken at 25 degrees Celsius or 21. But for this course, you don't really care about this, okay? What we care about is that for R, it's gonna have a specific rotation, the S will have basically the opposite specific rotation. If you have the two, they're gonna cancel each other, okay? And this is another way of testing. For example, let's say you made a sample, which for you guys you don't have to, and then you wanna make sure you have pure versus a mixture versus basically which isomer did you get. Sometimes you can look at the literature, they want to do the R isomer is basically the positive versus the negative, so you know which one you make. Or if you get a 0, you know that you have a mixture that you have to separate. This is important, especially when it comes to drugs, and I'll explain why in just a minute.
So, what if it's achiral?
It's a good point. What if the sample is achiral? It does nothing to the polarized
So
line.
it is
Stays at
the
0.
same thing. It's like we're so close to a mixture between two chirals.
Yes, if it's achiral molecule, so
How can I differentiate?
that's a good point. So when you have a mixture of two chiral, R and S, versus achiral, okay, how do you basically differentiate? Of course, when you test something, you should have an idea what this compound is in general. Okay, so let's say I'm trying to make basically an enantiomatically pure sample. Okay, one of the enantiomers, or I make the synthesis and I put it in the parameter and I get 0. Okay, there is two possibilities, right? Whether I have the two, the R and S,
Chiral?
basically the two
Opposite
chiral
of
centers
each other.
opposite each other as a mixture, or I didn't make what I want to make. Basically, it's still a chiral molecule at the end. So then you can take NMR, there's other instruments that you can use. But this is a quick way to tell you if you make a active, basically optically active compound or not, chiral or not. It's a mixture you have to investigate further. Okay? And another way is actually to test this, which is very easy, is you find in another chiral molecule that can interact with one of those. For example, if you have a specific, a lot of time proteins and enzymes can actually only interact with a specific enantiomer, not with both. So if you know which can interact with this molecule, if you interact it with the mixture, basically you may only trap one but not the other. There's another way to test this. But the quick indication if you have a chiral molecule is you just put it in the machine to see if it polarizes, if it rotates polarizes or not. Okay? But it's beyond, like I said, the specifics is beyond this course. So now, what is a chiral molecule? We said before, a chiral molecule normally it's asymmetric, lacks of symmetry, and normally it have 4 different groups around the central atom, right? Four different groups around the central atom, or the stereocenter. And we said